Hello everyone. So welcome to the second video of Unit 3, video 11. This video is about two topics, continuity, or the property of being continuous, and interval notation. So these topics kind of don't really go together all that well, but continuity is sort of the next thing, and we're going to need interval notation when we talk about the stuff in the video after this. So that's kind of why I'm putting those two things together right here. All right, let's get started. So continuity. All right, so this is going to be a super important thing to take notes, and in fact, this is another pretty conceptual video, so I'm going to be expecting those notes to be awesome. So let's start with a function, f of x, and I'm saying this is a function with real number inputs and outputs. You're going to see me say that a lot. Basically, that just means a kind of function that has a graph and not a super abstract function. Okay. So now I'm going to take this function and I'm going to fix a value for x and call that fixed value a. And there are three conditions for that have to be true for us to say that that function is continuous at x equals a. So I'm going to walk through the three conditions. The first condition is that f of a exists. All that means is that a is a valid input, and in other words, a is in the domain. The second condition is that the limit of f of x as x approaches a also exists. Okay, so this ties back to what we were talking about in the last video. So you can take the limit as x approaches a, and there's no plus or minus on that limit, so it's a two-sided limit. So the two-sided limit has to exist. Remember, that means that the limit from the left has to be the same as the limit from the right. Okay. The last condition is that these two things, f of a and this two-sided limit, have to equal each other. Okay. Now, that seems like a lot to remember, and in fact, I really could have actually just given you this third condition, because if you think about it, in order for those two things to be equal to each other, they both have to exist, right? So it doesn't really seem necessary to have 1 and 2. But I do think that 1 and 2 are very important to keep in mind, because actually most of the time when a function is not continuous, it will be because of 1 and 2, not actually because 3 is the one that's not satisfied. And we'll see that in the examples later on. But if all three things of these true, so I'm going to go through them again. F of a exists, the limit also exists, and they're equal. If all three of those are true, then we say that f is continuous at x equals a. So let's go straight to the graphs so we can see some examples of things that are and are not continuous. Okay. So in all of these examples, the a that I have fixed is 2. Right? And in fact, there's a lot of similarity in the way that I've constructed these graphs, but they all, you can see all the examples of being continuous and not being continuous in this example, right? So I'm just going to basically zoom in here so that we can see this, and I'm going to start over on the left. Okay, so over on the left, I actually have basically just taken a parabola, and remember a equals 2. So I'm looking at this point and seeing that there's a point here, so f of that value exists. Also, x is, as x approaches 2 from both the left and the right, I'm approaching the same thing. And in fact, I'm approaching f of 2. So there's no problems here. The limit is equal to what the actual value is, so the function is continuous. Okay, pretty straightforward. If you have a smooth line like this, the function's continuous. So how can that fail? Well, here's one way it can fail. Let's look at the second one. If I can scroll over. Okay, this is being a little slow. All right, so the second one's right here in the middle. So what the problem is here is that there's a circle, an open circle, which means, if you remember, that the value does not exist at that point. There is no point on the graph right there. And so because that's true, our first condition fails. So once again, this is a case where the graph is not continuous. Okay, here we go. So in this third one right here in the middle, what's the problem here? Well, this time we have a value, right? It's that closed dot. However, the limit from the left is not equal to the limit from the right. So that two-sided limit doesn't exist because the left-hand limit's not equal to the right-hand limit. And so that condition 2 fails. So that's why this is not continuous. Okay. In this last example here, or this fourth example, this one is the kind of odd one out. So I have a value. It's down here. The y value is negative 1.5. And I actually have a limit as well, because from the left and from the right, y is approaching this value 1. But those two things are not equal, right? 1 is not equal to negative 1.5. And that's where I have condition 1 and condition 2, but I don't have condition 3, that equality. Okay. In this very last example, so this time around, I basically made a piecewise function. And in this piecewise function, I have a value, and I also have a left-hand limit and a right-hand limit, and this time they're the same. So this is a case where I have a piecewise function, but the function's actually continuous because the value is equal to the two-sided limit. Okay. Now there is a general rule of thumb for this. I think it's really important to go through these examples and see if they fail, which condition fails, and if they succeed, why they succeed. So I think just to remind you guys, the first one and the last one are both continuous. The middle 3 are not. And you should go back to the previous slide and see which condition's failing for those middle 3 if you don't see it yet. But there is a rule of thumb. And that rule of thumb is if you can draw a graph through the point without lifting your pencil, then the function has to be continuous. Okay. Now that's not a very precise condition for doing precise mathematics with. You couldn't really prove very much from a definition like this rule of thumb, but it is a very, very useful thing to keep in mind. And people and mathematicians, when they were first thinking about this concept of continuous, they thought of it this way. They didn't think of it in the more complicated way. All right. So with that in mind, I'm going to switch to talking about interval notation. Okay. So we've been talking about sets of numbers in this class from day 1 pretty much, because in day 1 we were doing problems like finding the domain of functions, and we had to describe those domains using, well, any language we could. I was very free about which language we could use to describe those domains. But today I'm going to talk about a specific way that we can describe those sets, such as domains, and also sets like what we're going to be seeing in the next video. And that is interval notation. Okay. So an interval is basically the set of numbers between two values. Okay. And I think the best way is to go straight into the examples here. So all 3 of these examples that I've written here are intervals. And the way I've written them over here, so let's take a look at the first one. There's the interval between -1 and 3. So -1 less than x, less than or equal to 3. Okay. Can also be written in interval notation as parentheses -1, 3 brackets. Okay. So interval notation, you're using parentheses and brackets, and they have different meanings. And we're going to go over this in a second, but I think it's important to see more examples first. I've drawn out each of these 3 intervals on the number line 2, because I know it helps to think about things visually sometimes. And so what I see here is I'm looking at the numbers between -1 and 3, not including -1 because of the less than, but including 3 because of the less than or equal to. And we use those open and closed circles just in the same way we use them on graphs, meaning whether something is included or not included. Okay. And that's exactly what the parentheses and the brackets mean. The parenthesis means I'm not including it. The brackets mean I am including it. Okay, so let's go over the next two examples really quickly. The next example is the number set between 3 and 7, where I am including 3 and I'm also including 7. And because of that, I'm using brackets for both. Okay. Visually, I would draw this as a closed circle in both cases. So those are two intervals between two numbers. But we can also have an interval that goes all the way out to the end of the number line, which is minus infinity or infinity. And in that case, say I want to describe the set of numbers less than 4. Okay, so there's no left endpoint, so it keeps going on all the way to minus infinity. So to put that in interval notation, I have to say parentheses minus infinity, comma 4, parentheses. Okay. Now I have to put a parentheses here because I'm not including minus infinity. Minus infinity is not a number, so I can't include it in a set of real numbers. So if you ever use infinity or minus infinity, it has to go with a parenthesis. Okay, so I'm going to restate all what down here is I restate all the rules that I just said. Parentheses mean that it doesn't contain that endpoint. Brackets mean that it does. Okay. Now, I'm going to throw a couple more words into this. An open interval is one that doesn't contain either of the two endpoints. Okay, so one where I had parentheses on both sides. A closed interval is one that does contain both endpoints. So this second example here, because I've got closed circles on both sides, or brackets on both sides, that is a closed interval. This last one isn't actually an example of an open interval because it doesn't contain either endpoint. It doesn't contain 4, and it also doesn't contain minus infinity. This first example, because it contains one of the endpoints but not the other, is one that's actually considered neither open nor closed, and that is possible. It's a little frustrating because you think that everything should be either open or closed, but that's just not true. So this is a good place to kind of pause, make sure you get this written down, and think through this and make sure these words make sense. It's a lot of terminology, but it's going to help us write sets. Okay, so lastly, I'm going to give an example of using interval notation to do a problem that we've already done, which is actually good review because we could probably use seeing it again. And that is to find a domain of a function, but to put that domain in interval notation. So we're kind of coming around full circle here. I guess pun sort of intended. All right, so let's find the domain of this function. This function is square root of x plus 2 over x minus 1. So I'm going to actually do something a little different here. I'm going to write this on the screen, so it's going to be big, and I unfortunately the handwriting is not going to be too good, so bear with me a little bit. So this has a square root and it has a fraction. So we have to deal with these one at a time, as you might remember. So because of the square root, what's the rule behind the square root? The rule is that what's in the square root has to be greater than or equal to 0. Okay, so I'm going to write that out. Oop, I got to hit draw. X plus 2 is greater than or equal to 0. Okay, so that's one thing. The other thing is I have that fraction, and the rule with fractions is the denominator cannot equal 0. So I'm going to write that denominator, x minus 1 cannot equal 0. Okay, now in both of these, I can solve for x. So I can subtract 2 from the first one to get x is greater than or equal to minus 2. And I can add 1 to the second one to get x is not equal to 1. Okay. So this is one way to say this domain, right? That x has to be greater than or equal to minus 2, and it can't equal 1. Now let's take that set and put it in interval notation. And if you're struggling to do this, it can help to draw the picture. The picture is not essential to this problem if you can see it otherwise, but if you do get a little stuck or you just want to make absolute sure, then we can draw the number line. So let's do that. Okay, and the two relevant numbers that I see here are minus 2 and 1. So I'm going to draw them in that order because minus 2 is to the left of 1. I'm pretty sure about that. And now let's account for both of these. So the first one is saying that x has to be greater than or equal to minus 2. So that's a closed circle this way. Now, also x can't equal 1, right? So, oh, there it is. I need an open circle at 1. Okay, yikes, that didn't look super great. So I would encourage you to spend a little more time on your drawing than I did on mine. So, what do I see here? I see that x has to be to the right of minus 2, and minus 2 is okay because of that greater than or equal to, but I can't equal 1, so I need an open circle there. So I've got 2 intervals going on right now. And I'm going to write out both of these. So the first interval here is between minus 2 and 1. Okay, so how do I express that? Well, it contains the minus 2, so I use brackets, but it doesn't contain the 1, so I need a parentheses there. Okay, but I'm not done yet because I also could have a number bigger than 1. So, and I have the interval that starts at 1, not including 1, and it goes all the way out to positive infinity because there's no right endpoint. Another way to say that is that the right endpoint is positive infinity. And I can't contain positive infinity, so I have to put a parentheses there. Okay. So part of the practice for next time will be to do a couple of these domains with interval notation to get a little bit of extra practice. Feel free to ask the question in class, as always. Thanks for watching. I will see you in class.